Okay, we are now going to move on to a very important subject within the context of this module. This is the topic of calculus. So what are we going to be doing here? Before I start, I'm going to give another pretentious quote, something which I think is rather appropriate, something which you may well be feeling with vague memories of calculus. And one and all, they had a longing to get away from this painfulness, this ceremony, which had reminded them of things they could not bear to think about, to get away quickly and go about their business and forget. It's from The Foresight Saga, which I highly recommend to anyone who's not familiar with that particular work. Okay, let's move on to the main subject matter. What's our interest in calculus? Calculus, when we look at it in rather more detail, is really concerned with the topic of dynamic behavior as opposed to static behavior. So if we look at what we've seen so far, the models we've looked at, numbers, polynomial structures, even vectors and matrix vector structures, they're a little bit static. They're quite fixed objects. They don't really change in form. So, for example, we've seen how to evaluate a polynomial expression at a given point, at a given value of x. What we haven't done, though, is looked at tools which analyze how the behavior of that polynomial changes as we change the input values to that polynomial. So differential calculus, which is what I'm going to be talking about in the first part of this section, its origins are in trying to find a rigorous mechanism by which we can study change in behavior. So before we go on to look at how differential calculus develop such techniques, important initial notion we have to look at is that of a function. And all a function is, it's just a formal way of saying, a formal description of how a given input value should be processed in order to produce a particular output value. Input values normally have to satisfy some conditions. They're restricted to those that fall within some set of values. That particular set we refer to as the domain of the function. Output values, in a similar way, these have to fall, these are required to come within some output set, what we refer to as the range of the function. So a function whose domain is D and whose range is R, we write that using this formal description here. F is a function that takes values in a particular domain and produces output in a particular range. At this stage, we're only going to be interested in functions whose domain and range are the real numbers. So here are a few examples. In the last section of the module, we met this notion of polynomial functions. I'm sure many of you from school are familiar with what are called the trigonometric functions, such as sine, cosine, tangent. We also have, which I believe Professor Kerner may have mentioned briefly in Comp 109, logarithmic and exponential functions. The logarithm, the natural logarithm, the exponential function. We have rational functions. We take one function and we divide it by another function. We are what are referred to as radicals, roots. So we take some input value and we look at a particular root of that function. Now, one characteristic we notice about all of these is they have very different behaviors. Some we can report an output value irrespective of what the input value for that function is. So they are what is called well behaved for all input values. Some of these functions don't have a defined output value for certain input values, for particular real values. Some of these functions we can get as a result any real number whatsoever. Others, we may only get results that fall within a particular interval, that have a certain range of reals as their result. So, if we look at these examples in more detail, take polynomial functions. These are what are called well-behaved regardless of what the input value to those functions is. So if we take any polynomial function, we take any real number, then we can define the value of that polynomial function with that input value we've given. In contrast, if we take trigonometric functions, well, if we look at the sine and the cosine function, the output value of those functions always lies within a restricted range of values. That is always at least -1 and at most +1. In contrast, if we take the tangent function, we can get as an output from the tangent function any real value, negative or positive. We look at the logarithm and exponential functions. These again have very different behaviors. The exponential function, regardless of what input we supply to the exponential function, we always get a positive, a greater than 0 output. For the logarithmic function, it doesn't matter whether we mean common log, natural logarithm, the logarithm function, it doesn't have a defined behavior when the input value we give it is not positive, when it's less than or equal to 0. We take rational functions. Once again, these do not have defined behavior when the denominator function is such that it takes the value 0 at a given point. Look at finally radical functions, as we'll see in the next part of this module. Their behavior is not well defined for particular values of the radical and for particular inputs. So for example, if we're dealing with the case of square roots and we have a value for the input which is less than 0, we do not have a defined real output in that particular case. The class of functions which are of particular interest with respect to differential calculus are what we call linear functions. So these are functions that have the form: the output of the function is given by multiplying its input by some constant value and by adding another constant value to that outcome. And one way we often write that is we are treating the input value as a coordinate going horizontally, and we want to treat the output as the second part of a coordinate pair measured vertically. So this tells us, given this coordinate on the horizontal axis, how to compute a corresponding value on the vertical axis. Now, it doesn't matter which value in the real numbers we give on the horizontal axis, we will get a unique outcome for the vertical axis. Any value on the horizontal axis defines a unique pair as a coordinate on the two-dimensional coordinate axes. Now this parameter, this value with which we multiply our input value, this is referred to as the gradient of the line function. And this notion of gradient is something we're going to be meeting quite a lot as we continue with the study of calculus. The other part, the value we add to the result of multiplying our input value by the gradient, this is called the offset of the line function. Very informally, differential calculus is concerned with the behavior of the gradient of lines which are related to functions in a particular way. So before I go on to talk about that, let's have another look at properties of linear functions in more detail. So first of all, suppose we have any two distinct points in the plane, such as these two. There is a unique line function which joins those 2 points, which connects this point to this point. Suppose we're given any single point in the plane and a value for the gradient. Once again, there is a unique line function whose gradient is the value specified and which contains this point that we've given. Finding gradients, this is a basic notion in calculus. This idea of computing gradients underpins differential calculus, as we'll see. So, how do we go about computing gradients? So suppose once again we have any two distinct points, this one and this one. What the gradient is measuring is how much the vertical distance should change, the height, compared to changes in the horizontal distance. In other words, suppose we have 3 points, this, and this, and these are all on the same line. They are what are referred to as collinear points. Then, assuming we've ordered our points by increasing horizontal value, this is greater than this is greater than this, then one property of gradient and line functions is the gradient of the unique line connecting this point to this point. That's exactly the same as the gradient of the unique line connecting this point to this point. In other words, what our notion of gradient is capturing is how much the vertical value should change relative to how much the horizontal value has changed. What does that tell us? That tells us that the formula for calculating the gradient of a line between 2 points is just this. The gradient of a line is how much the vertical distance should change, this minus this, divided by how much the horizontal distance has changed, this minus this value here. So that's our formula for computing the gradient of a line connecting 2 points. We want to compute the offset. Well, all we need to do in the offset is just the vertical distance corresponding to a horizontal distance of 0. In other words, this constant value for which the gradient, which we've already discovered, satisfies this relationship here. And we're assuming, of course, that we are starting from a place other than 0. So how are gradients used in differential calculus? The particular class of gradients that we're using, when we analyze a function, we are interested in the gradient of the line that touches the curve described by the function at a particular point. Such gradients, we have a special name for the function that captures this gradient. This is called, if we are given the function f, the first derivative of f. And there are various notations which are used for that function, the first derivative, either this form with the dash or this dy by dx form. I'm going to avoid using terminology which some of you may have heard at school. The terminology I am going to avoid using is referring to gradient of the tangent. I'm going to use something which means exactly the same, gradient of a line touching a curve at a particular point. And what I'm going to look at in the next lecture is how we go about computing those functions, those derivatives. In other words, given some arbitrary function, how do we find this function corresponding to what I'm calling the first derivative of that function?